Okay, welcome back. This is 7.1 on functions on general sets. First, we'll define what a function is. And we have some notation also to deal with, and also there's complications arising from the fact that we have multiple definitions, multiple terms for these objects that we're dealing with. Okay. So anyways, the first thing we'll look at is a function f from a set x to a set y, which we will symbolize as this. So a function f going from some set x to some other set y. Okay. This x set is called the domain. You're probably familiar with that word, not as familiar with this other word, codomain. Codomain is a more general way of talking about this y set. Usually you call it the range, but the problem with the range is the range might be a subset of the codomain. So for example, the range of the function y equals x squared is all real numbers from 0 to infinity. So if your codomain could be the real numbers, the actual range in that case would be a subset of the codomain. Just the real numbers from 0 to infinity as opposed to the real numbers from negative infinity to infinity. Okay, so it's a small detail that you kind of have to deal with. Okay. Anyways, a function, how are we going to define it? There's two aspects. Probably the first aspect you're as not familiar with, and that's every element in the domain has to go to or have a corresponding element in the codomain. So we'll just say is related to some element in the codomain. Okay, and then the statement that you're used to is that there can only be one element in the codomain that's related to that element in the domain. Okay, so we'll say no element in the domain is related to more than one element in the codomain. Okay. Okay, and that's basically just your vertical line test. Okay, so you're not going to have a vertical line hitting the graph in more than one place. Okay, it's kind of that thing that you're used to. That's the way maybe you saw it in pre-calculus. Okay, okay, so there's the codomain. Let's define then the range of f. And this is in terms of sets, and we also call this sometimes the image of the set x under f. Okay, and I think maybe the book has maybe one or two other ways of calling it, but it'll be a set of elements y in the codomain such that y is equal to f of x for some x in the domain. So we'll just say some x and big X. Okay. You can also talk about single elements, and that's the f of little x that you see sometimes. So f of x is the image of little x under f, and that will just be a single element as opposed to a set of elements. Okay. Then the other guy, the inverse image of y, is going to be the set of all x in the domain such that f of x is equal to y. Okay. For some y in the codomain. Okay. We could talk about single objects again here, and we'd say when f of x equals y, x is an inverse image of y. Okay, so a lot of definitions just thrown at you all at once at the beginning of this section. Let's look at problem 1 in the book, and just doing an example will help you a lot. Okay, kind of figure out your left from your right, so to speak. Okay, so they give you the domain 1, 3, 5. Their codomain, so S, T, U, V, and we're dealing with the function f, which is going from the set x to the set y. Okay, and they describe it with these arrow diagrams, and we could draw it like this. So I'm going to put the codomain over here, 1, 3, 5. Or sorry, the domain over here, and then the codomain over here, so STUV. And the book tells us we have this arrow from 1 to V, and then we have an arrow from 5 to V, and then we have an arrow from 3 to S. And this describes the function. Okay, so part A, we want to know what the domain is, and of course that's just going to be the domain of f is just going to be the set x. Okay, so it's just 1, 3, 5. The codomain, which I think they also asked for in part A, codomain, is just going to be the set y. Okay, so S, T, U, V, everything. Part B, then they ask about the image of some x values under f. So for instance, f of 1 equals what, f of 3 equals what, and then f of 5 equals what. Okay. So you just use the arrow diagram and follow the arrows, right? So f of 1, I guess I'll draw it on here. So f of 1 here is going from 1 to v, so f of 1 must be v. And then likewise, f of 3 must be s, and then f of 5 is also v. Okay. Part C, they want to know then the range of f. Or the image of the domain under f, and this time it's a subset of the codomain, right? So these are the objects that actually have arrows pointing at them, and it's just going to be the set of S and V. So definitely compare that range set here to this codomain set. Okay, and note that this range is a subset of the codomain. Then they're going to want for you to find inverse images. So the inverse image of yes, particular y values. So this is part D in the book, and part E. Just sort of group them together. So first they want the inverse image of S. And what you just do is go back to the diagram and go backwards from S, right? So the inverse image of S is 3. And here we want a set, not just an inverse image of S, but the entire set. Okay. Then, inverse image of U. Okay, so you go back to the diagram. There's no arrow pointing at U. Up there at the top of the screen, there's no arrow going to U, so you're just going to put the empty set, the null set. The inverse image, we'll just do one more, of I guess V, And V has two elements going to it, so 1 and 5 will go into that set. Okay. Okay. Then part F, they want you to write the function as a set of ordered pairs. So F is going to equal, and what you do is just put all of the endpoints of the arrows into here. So 1 comma the yellow arrow and the diagram at the top there is going from 1 to V, so you would put 1 comma V. There's an arrow going from 5 to V, so you put 5 comma V, and then the last arrow 3 to S, so you put 3 comma S. Okay. So a function is a special kind of relation, and a relation is a set of ordered pairs. So we'll write 1 to V, and then 3 to S, and then 5 to V. Okay. Figuring out if two functions are equal to each other can be interesting. So test for functional equality. And we'll take a look at an example that's a finite example, and all you're doing is basically going through every possible value of x and making sure f of x is equal to g of x, and if that's true for all of them, then the functions are equal. Okay, so in particular, let's look at 14. They're going to give us a set which they're calling J5. So 0, 1, 2, 3, 4. Which is just okay, so and then the others, yeah, that's our set, and then we want our function to go from J5 to J5, and then the other function K is going from J5 to J5. And what are the functions? So h of x is equal to x plus 3 cubed mod 5. K of x is equal to x cubed plus 4x squared plus 2x plus 2 mod 5. And so what we need to do is, in order to show, so what do we want to show h is equal to k. And in order to do that, we have to go through every x value and show that h of that x is equal to k of that x. Okay? So I'll just make a table here. And I need to go for every j. So 0, 1, 2, 3, 4. Okay. And you're plugging them into the function. So h of 0 is going to be 0 plus 3 cubed mod 5. 0 plus 3 cubed is 3 cubed, which is 27. And then to take it modulo 5, you figure out how much do you have to subtract from 27 to make it divisible by 5. Okay, and the only numbers you can use to subtract are 0, 1, 2, 3, and 4. Okay, so if you subtract 27 by 2, it'll be 25, and that's divisible by 5. So I'll just say this is kind of equal to, and I use this triple bar to say it's equal in this setting, modulo 5, to 2. Okay, okay, so let's try another one. So this one is 1 plus 3 cubed. That's 4 cubed. 4 cubed is 64. Okay, and if you subtract away 4, that's going to be divisible by 5. Okay, so we'll say it's equal to 4 modulo 5. Then 2, so 2 plus 3 cubed is 5 cubed, which is 125. That's divisible by 5. So 125 minus 0 is divisible by 5. So that's, they'll say that's congruent to 0 modulo 5. Okay. 3 plus 3 cubed is 9 cubed. 9 cubed is, I'm not even sure what that is. 1 times 9. The last number is a 9. So if you subtract away 4, that'll be, so wait a second, 3 plus 3 is 6, sorry. 6 cubed. So 36 times 6 will end in 6. So that's modulo 1. Okay. So it's something that ends in 6. When you subtract away 1, it'll be divisible by 5. And then finally 4 plus 3 cubed is 7 cubed. So 49 times 7 will end in a 3. So that will be modulo 3. Or sorry, congruent to 3 modulo 5. Okay. Let's go through the other guys. Okay, so and again, you know, how do I figure out what 27 mod 5 was? Okay, what is that? Well, it's you want to take 27 and subtract something away. Okay, so x, which will be equal to 5 times some integer value. Okay, and you want the smallest value of x that will allow you to do that, will allow you to have that. So if you take 27 minus 2, that'll be divisible by 5. In other words, it'll be a multiple of 5. So it'll be 25, which equals 5 times some value k. So this is equal to 2. Okay, it's also the remainder of 27 when you divide it by 5. Okay, but there's another way of thinking about it, and that's kind of this modulo type thing that I'm thinking of, which I remember from number theory, and I know you haven't taken that, so I apologize. But again, we dealt with it in the Euclidean algorithm, so it's just the remainder when you divide 27 by 5. Okay, so the remainder when you divide 64 by 5 is 4. The remainder when you divide 125 by 5 is 0. The remainder when you divide whatever this number was by 5 is 1. When you divide whatever this number was by 5 is 3. Okay, so let's go to the other one. So now I'm plugging these x values into my k function. Okay, so 0 cubed, that's going to be 2 mod 5. So that will just be 2. Put in 1, you get 1 plus 4 plus 2. So 4, 5, 6, 7, 8, 9. So that'll be 4 modulo 5. And then plug in 2. So that's going to be 8 plus 16 plus 4 plus 2. So that would be 20 plus 10. That's 0 modulo 5. Then put in 3. That'll be 9 plus, 27 plus 9 times 4 is 36 plus 6 plus 2, so 6, 7, 8. There would be a 4 and then a 1. Okay, all you really need to do is look at the last digit, and so there's clever ways of figuring it out. You may have to do it the long way, but if you plug in 4, you'll get 64 plus 64. So that'll give you your end digit is 8, and then plus 8 plus 2. So this end digit is 10, so 3. 18, so you'd have the last digit would be 8 of this sum, and then 8 minus 3 is divisible by 5. Okay, so that would be how to think of that as well. So anyways, long story short, they're all the same, so hence h of x equals k of x for all x in our domain, which was J5. Thus, we can conclude h is equal to k. Right? So it definitely would be a lot harder if you have an infinite set, and it would probably require some different approach. I'm not going to worry about that. Oh, and it's not in the homework, so we'll just go on to something else. Examples of log functions. The logarithm is a nicely behaved function. It's increasing. It's 1 to 1, so it has an inverse as well. So this will come under the title of examples of functions. So logarithms, they'll give you a definition. There's all kinds of restrictions on logs, so we need to let b be in the positive reals. B can't be equal to 1, and x is in the positive reals. And in that case, the definition of a log is log base b of x is equal to y if and only if b to the y equals x. Okay, so that will be our definition that we can use in proofs. Let's look at one particular proof, problem 21. We'll presume b is in the positive real numbers. B is not equal to 1, and x is any real. Supposing all that's true, then we can conclude that b to the negative x is equal to 1 over b to the x. Okay, so that's just a rule of exponents. What do we want to do? We want to prove for all u and the positive reals, b and the positive reals, and b not equal to 1, that log base b of 1 over u is equal to negative log base b of u. Okay, so it's a rule of logarithms you learn in pre-calculus, and maybe they just handed it to you. We want to actually be able to prove this now. Okay, so we'll go ahead and make our suppositions. Suppose then that u is in our plus the positive reals, b is in the positive reals, and b is not equal to 1. We'll go ahead and instantiate the c value, which will equal the log base b of 1 over u. Okay, we want to use definitions, and so the definition of logs and this rule of exponents that I introduced here in the beginning, in order to prove that this z thing is equal to negative log base b of u. Okay, so we first note by definition of logs, we can rewrite z, okay, z equaling log base b of 1 over u. That equation, we can rewrite it as b to the z equals 1 over u. Okay, then we could use that exponent rule that I introduced up here, and rewrite this as 1 over b to the negative z. Okay, because z is the same as negative z, so it's like a double negative rule, and so that'll be 1 over b to the negative z, which is really 1 over b to the negative z. Okay, and that'll equal 1 over u. And then I can multiply both sides by b to the negative z, and I'll get b to the negative z equals u. Okay, and then I can do definition again, definition of logarithms, to rewrite this, right? So log base b of u is equal to negative z. And then you could do a substitution. Now we can kind of go back here to z and dump that expression in for z here. Okay, so we'll end up with log, whoops, let me go back to the other color. Log base b of u is equal to negative log base b of 1 over u. And we almost got it, right? So what we're after is kind of the same equation up here at the top of the screen, the same equation but with a negative on the other side. And that's easy to remedy just using properties of equations. You can multiply both sides by a -1, and you end up with, and flip-flop sides, log base b of 1 over u is equal to negative log base b of u, okay, which is what we wanted to show. Okay, so just using definitions and rules that we've learned in basic algebra, we are able to prove these logarithms, these log properties. Okay? And some of those proofs are a little weird. It's kind of like, I don't know where they begin, I don't know where they end. But you'll get used to them after a while. You'll get used to it. Anyways, part B, we talk about there's some problems in there with Hamming distance and encoding. So you're sending strings of data long distances, and the strings of data can be thought of as zeros and ones. I guess they'll probably be electrical impulses, on and offs. The problem is, as they travel long distances, they collect error, and you want to be able to kind of identify the error. So what they do is kind of rewrite the strings in triplet form, and then use Hamming distance to kind of figure out where the error is, and then they can kind of figure out what the original message must have been. Okay, so in order to encode a string, a 4-digit number here, we're going to replace every one with 3 times itself. So instead of writing 0, I'm going to write 0, 0, 0 for this guy. Instead of writing 1, I'm going to write 1, 1, 1 for the second guy. For the third guy, write 1, 1, 1. And then for the last guy, I wrote 0, 0, 0. And that's it. Okay, so it's just that easy. Going in reverse, then, if you have 1, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, you can just rewrite the first group as 1, the second group as 1, the third group as 0, and the fourth group as 1. Okay. Then the Hamming distance measures the difference between strings. Okay, so you're kind of thinking about error accumulating. And just part B, I don't think there's any Hamming questions on the actual homework, but just for people that are interested, and I've never studied this at all. I've had friends that did, but I never did. So what you're doing is kind of comparing the strings and seeing how many are different. So this compared to this, that's 1. These are the same. Okay. This and this are the same. This and this are the same. And then this and this are different. So the Hamming distance is 2. Okay. And you could probably define that as some sort of, I don't know if you could define that as a metric, and then do kind of calculus on it. You might be able to. I don't know. Like I said, I never studied it. Seems like that would be an interesting topic to study, though. One other thing that comes up all the time in like analysis classes and abstract algebra classes is a function that's not well defined. Okay, and there are 2 things that would cause something not to be well defined. And first off, basically there's nothing in the there's no outputs for certain inputs. Okay, so there's basically no y for a particular x in the domain. Okay, so imagine a function going from the set of integers to the set of integers, and then that function is we could define it as f of x equals the square root of x, right? So in this case, there's no output for when x equals 2, right? Because there's not going to be any, when you put 2 into this function, it'll be the square root of 2, which is not an integer. Okay, so we'll say that's not well defined. The other case is when it's not a function itself. So you'll have 2 outputs for one x value. So you have 2 different y values, different y values for the same input. Okay. And an example of that would be something like number 33 in the book. And in the homework, they'll have you basically figure out a bunch of functions and kind of work with them. But g of going from the rationals to the integers defined by g of m over n is equal to m minus n. Okay, and the problem here is you can have 2 of the same thing going to 2 different places. So imagine g of 5/10, which is the same as g of 1/2, right? 5/10 is the same as 1/2. But using the definition, you'll see you get 2 different values. So they'll say it's not well defined. G of 5/10 is going to be 5 minus 10, which is negative 5. But g of 1/2 is also kind of a different thing. It's 1 minus 2 is negative 1. These guys aren't the same, so it's not well defined. Okay. The last set of problems, we kind of deal with functions on sets. So section 5, functions on sets, and we get some more definitions here. In particular, if f is some function going from the set x to the set y, and then we look at some subsets of x and y. So A is a subset of x, and then let's say C is a subset of y. Then we can consider a function on those subsets. So we'll say the image of A under F is written as f of big A. Okay, and that will just be the set of all y in y, such that y is equal to f of x for some x in A. Okay. And then we can also think about the inverse image of C, which we will write f inverse of C, and that'll be a set of x values, right? So it'll be x in the set big X, such that f of x is then in the subset C. Okay, and then there'll be little proofs where you have to kind of chase down variables. So we'll look at one little proof. This is number 45. We want to prove for all subsets C and D of the codomain Y, if C is contained, so if C is, I'm running out of time, so I'm trying to hurry, I apologize. So C is contained in D, then big F inverse, we'll call it, of C is contained in big F inverse of D. Okay, so the way you want to do this is kind of take an arbitrarily picked element, a particular but arbitrarily chosen element in here, and then show that it's going to be in here. Okay, and you have to be worried. So what would an element in f inverse of C be? Well, that would be not a y element, but an x element in the domain, right? So it'd be an x element in the domain such that f of x is in the set C. Right, so you have to do multiple suppositions. So suppose first that C and D are subsets of Y, and also C is contained in D, and then we're going to suppose X is a particular but arbitrarily chosen element in that thing I put in the box in this f inverse of C, in the set f inverse of C. Okay, so by definition of big F inverse of C, X is an element in the domain such that big F of X is in the set C. Okay, then we could say, or thus, by the definition of containment, big F of X must also be in D, because we presumed back here to the left here that C was contained in D, and here f of X is in C. So if f of X is in C, then f of X must also be in D by definition of containment. So f of X is in D. Okay, And then we could say hence x is an element in the domain such that big F of x is in D, and by then definition of big F inverse of D, that means that x is in big F inverse of D. Okay, so by definition big F inverse of D. Okay, so big F inverse of D is the set of all x in the domain such that f of x is in D, right? And that's kind of what we just wrote out. X is an element in X such that f of x is in D. So by definition, maybe I can even just cut to the chase, right? By definition, then X is in F inverse of D. Right? So when X is in F inverse of C, X is then in F inverse of D because X was arbitrarily chosen. It means that F inverse of C is contained in F inverse of D. Okay, they're weird proofs, but if you're going into a class like real analysis or topology or something like that, you really need to kind of wrap your brain around it. And it's a practice. You have to have practice at it. You have to do it. There's no way around it. And the homework, these are the kind of questions where you just kind of pick and choose. They'll give you a list of steps in the proof. So like problem number 17 here. So you kind of just want to go through and chip away at it. So you suppose what are we trying to prove? That f of A intersect B is contained in f of A intersect f of B. So they give you the supposition A and B are subsets such that Y is any element in f of A intersect B. Right, so there must be some x in A intersect B such that f of x is equal to this y. So there must be some x in A intersect B such that f of x is equal to that y. And then I guess x is in A by definition of intersection. F is in x. X is in A and x is in B. So there must be some element x in I hate these problems. Okay, so f of x, by definition of image, then f of x is in f of A and f of x is in f of B. So by substitution, then you could say because f of x is equal to y, that y must be in f of A and y is in f of B, and then it would follow. Okay, so I wouldn't expect you to get that on your first try. You're probably gonna have to submit it once or twice. Okay, on a test, you just do the best you can and hope it works. But okay, so I'll cut it there, and we'll see you next time. Okay, thanks for watching.